Alright guys, welcome to this page of the notes. And what this page of the notes does is it describes for you the solution intervals when you're solving a quadratic inequality in one variable. However, if I try to explain it to you without having done an example problem or really sort of understanding the idea here, it would just be incredibly confusing, which is sometimes why kids really struggle with reading a math textbook. Sometimes the book definitions and the way they explain things are really kind of confusing if you haven't seen someone work through an example problem first. So that's exactly what we're going to do. I'm actually going to jump ahead. I'm going to do a problem with you. All right? I'm going to show you how it works. And then I'm going to come back to this and show you how this is the definition that allows us to solve the problem. It's kind of working backwards, but I promise, I swear, it'll make more sense if we do it that way. So stick with me, and let's try this example problem right here. Now, because I kind of goofed. I don't know why I did this, but I did. I say solve this quadratic equation in one variable by graphing. We are going to graph, and I gave you a coordinate plane, which makes you think, oh, he wants me to graph it on a coordinate plane. I don't. What I should have done is I should have given you a number line. Now, for this first example problem, I will go ahead and graph it on the coordinate system for you because I do want you to see how it relates to our textbook definition. But for the rest of the problems, I'm not actually going to graph it on a coordinate plane. We'll only need a number line. And so when I say graph, just know, please just know that what I actually mean is graph on a number line. And actually, I'm the one who goofed up by giving you a coordinate plane when actually what I should have done is I should have given you a number line, and I didn't do that. So I apologize, but we'll work through it anyway. So here we go. The way that you're going to do these problems is this. What I have is a quadratic inequality, and I'm going to, for the moment, kind of initially here, I'm going to ignore that inequality symbol. All right, so I'm going to ignore the inequality symbol, and I'm going to do x squared plus 2x minus 3 is equal to 0. Well, we'll remember back to the first page of the notes that anytime you have a quadratic in one variable equal to 0, they want you to solve. We'll solve by factoring. We've taught you 6 different methods for factoring in this chapter. You could do GCF, difference of squares, perfect square trinomials, general trinomials, complete the square, or quadratic formula. Actually, in this one, I think just factoring it as a general trinomial will work, which is our fourth option. Since my leading coefficient is a 1, I just need an x and an x. And then all I need are 2 numbers. Those 2 numbers have to multiply to a negative 3 and sum to a positive 2, which is actually really very simple. I need a plus 3 and a minus 1. Positive 3 times a negative 1 is a minus 3, and a positive 3 plus a negative 1 is a positive 2. Well, now I use the zero product property to split these guys up. X plus 3 is equal to 0. X minus 1 is equal to 0, which means x is equal to 1, and x is equal to negative 3. Now I set up my number line, right? Graph on a number line. And I apologize I didn't give you one. That's okay. You can make your own. All right, so negative 3, well, let's put that somewhere over here. Positive 1, we'll put that somewhere over there, right? So negative 3 and positive 1, those are my 2 solutions to this quadratic. Now, what I'm going to do to solve the inequality, right, because I was given an inequality, I'm going to choose test points, and I'm going to check each of my intervals. I have this interval over here, from negative infinity to negative 3. I have this interval in the middle, negative 3 to a positive 1. And I have this interval over here, which is from a positive 1 to positive infinity. and I need to check each interval. I'll do that by choosing a test point, and of course we want to work smarter, not harder, so let's go ahead and use 0. We'll use 2, and we'll use -4. Now, all I need to do is plug each of those test points into my original inequality and see what it gives me. Let's start with the easy one, 0. 0, 0, that leaves me with a -3, and the inequality tells me that -3 is greater than 0. Is that true? No. No, -3 is not greater than 0, so that is false. Which means the region between -3 and +1 is not my solution interval, because I tested one of the points and it's a false statement. It didn't work. Let's try the other ones. I plug in a 2. Well, 2 squared is 4, and 2 times 2 is 4. 4 plus 4 would be 8, and 8 minus 3 is 5. Is 5 greater than 0? Yes. Yeah, 5 is greater than 0. So that is true. Well, there we go. I just found a solution region. It turns out -1 to infinity is going to be a solution region. Let's check -4. Well, I plug in a -4. -4 squared is 16. -4 times 2 would be a -8. 16 minus 8 would be a +8. 8 minus 3 would also be a 5. And 5 is greater than 0. So this turns out to be true as well. Now, here's how you're going to, shade or give me your solution regions. I'm going to shade everything that is true on my number line, and I need open circles because I'm strictly greater than. So it's going to be an open circle and an open circle, and everybody going in this direction and everybody going in that direction. Well, now hopefully what you guys will remember is this represents an OR inequality, because my solution regions are heading in opposite directions. You can kind of think of them as oars on a boat, If you're sitting in the middle here on the boat, your oars are sticking off the sides. It's an OR inequality. And we're going to write that in set builder notation, which hopefully you'll remember means that you need a bracket. You give me the variable, which in this case is x. The bar means such that, so it's all values of x, such that, and you're going to give me both inequalities. I need all values of x such that x is strictly less than -3. That's why I have an open circle, because it's strictly less than. Or x is strictly greater than a +1. And then close that whole thing off with another bracket. This is the answer that I'm looking for. And actually is going to be the answer that I'm looking for on the homework, on the quiz, on the test, Your answer is the intervals that represent the solution regions. What is a solution to this inequality? Well, you can pick any value of x you want to as long as it's strictly less than -3. It'll satisfy the inequality. Or you could pick any value of x strictly greater than 1. It will satisfy the inequality. So I have two solution intervals, -infinity to -3, and +1 to +infinity represented by the number line. And this interval notation represents those intervals, or interval notation, set builder notation represents my intervals or my solution regions. Now, what I told you guys I was going to do was tie this back to what they were talking about here in the book. Let me show you. I'm going to go ahead and graph this guy. All right, I'm going to graph it, and here's the way I'm going to do it. I'm going to go ahead and put this guy into vertex form, and then graph it by doing the transformations A, H, and K. So let me do that for you real quick. It's x squared plus 2x minus 3 is equal to y. That's if I were going to graph it. So x squared plus 2x minus 3 is equal to, actually, sorry, here, I should put the y on the other side. Yeah. All right, now, to put this guy into vertex form, I have to complete the square. Since it's y equals, I need to use parentheses so I can do all my work on the same side of the equal sign. My leading coefficient is a 1, so I'll add b squared over 4 inside the parentheses, which in this case turns out to be a positive 1. And to maintain equality, I'll subtract b squared over 4 on the outside of the parentheses, which means I subtract 1. I'm going to need a plus 1 and a plus 1. And what I see is a is equal to 1, h is equal to 1, and k is equal to a negative 4. So here's what I'm going to do. I'm going to go back to my coordinate plane, and I'm going to graph this quadratic. I'm going to shift horizontally to negative 1, shift down negative 4. My parabola is going to open up, and it'll just be a standard parabola. There's no vertical stretch or vertical compression. So let's go ahead and graph this guy. So like I said, it's going to shift horizontally negative 1 and then down 4. So right there, that represents my vertex. And then it's just going to be a standard parabola opening up. So 1, 1, 1, 1. And it's got to be a dotted line. Okay, now that I have graphed my parabola, right? I graphed my parabola. Here's what they're asking you to do. They want you, right, to find all of the values, right, for which the parabola is greater than 0. But they want to know where is the parabola above the x-axis, right? Where is this quadratic greater than 0? Well, if I'm using the x-axis, right, as my dividing line, which I am, right there is y equals 0. It's the x-axis, right? I want to know the inequality is asking me, where is my graph above the x-axis? Where is it greater than 0? Well, here my parabola is below the x-axis. So that's not my solution. Here my parabola is above the x-axis, and over here my parabola is above the x-axis. So the solutions to this inequality are the intervals where the parabola is above the x-axis, which would be an open circle here and an open circle here. Open circle because it's strictly greater than. And then everywhere where the parabola is above the x-axis, well, that's everybody headed in this direction, right? If I choose this value of x, I would trace to above the x-axis. Trace to above the x-axis, right, to get to my parabola. Here, trace to above the x-axis. Trace to above the x-axis, right? So everybody going in this direction. Hopefully what you see is a very good, well, not a very good, you see a similarity between what I have just done on this graph and what we did on the number line. The only difference, right, is that I've put my parabola in there, where when I did it on the number line, instead of drawing the parabola, I just simply chose some test points that I used to figure out whether that represented a solution region, which the middle did not. It does not. The outsides do. looks just like my number line, but here I graphed it. So here's what they were telling you back here on this previous page, right? If you were to take a look at this, and again, if I were to try to explain it to you without having done that example problem, believe me, we would have been lost and you would have hung your heads and be like, I just can't do this anymore. But you can do it. It's not that complicated. It's just the way the book set it up makes it a little tricky. So actually what we wound up with is this one right here, right? Where I graph my parabola, which is opening up, and my solutions are all the values of the parabola that are greater than 0. And so I wound up with my solution regions, right, going in opposite directions, or an OR inequality. So that's the one we had. There's actually 4 possibilities, and as we do the other example problems, we'll run into those other possibilities. So head on over to the next page of the notes. We'll take a look at another one of these. I'll see you there.